Hello, good evening, everyone. Am I audible and my screen is visible or not?
Yes, you are audible. I can see the screen.
So is the font size okay or should I zoom in?
Zoom in, please. It's a little small.
Okay. Screen?
Yeah, it's better.
Okay. When I zoom in, I am not able to write anything. Yeah, I'm. So should we start?
Yeah, let's start. It's already 8:05. So
We already did. Yeah. Okay. So now we are into week 6, and week 6 is all about the regularization. And so it's the continuation with week 5. So in week uh, what where we are and where we are heading. So in week 5 we have seen that we have training data set which are coming from some function, let's say f, some function f that we don't know, right? And our whole idea is to come up with a approximation to that function. And we want to find a function that can approximate the true function, right? Because we don't know the true function and we have only the training data set which are coming from that true function with some noise associated with those, right? Because there's some noise associated with those data points, and we have some bunch of data points only, not the true function itself. The approximation that we have done, the regression model that we have come up with, that can be is how good that function is, how good that model is, right? Or either that is close to true function or is far away from the true function, we never know, because we don't know the distribution of the function, distribution of the data set. We don't know which function has generated those data set, right? So how good the model is, that we need to answer. Okay, so that's what we are going to see in week 6, and how to if our model is not good, what are the different measures that tells us that this model is not good, is not performing well. Then how we can resolve those problems that we are gonna see in the week 6. That is called regularization, right? So what we have seen in week 5, we have seen the probabilistic view of linear regression model as well, right? Where we assume that our labels. Okay, so where we assume that our labels are associated with the features, right, in some manner. So we are assuming that y are coming from some function x, but with some noise associated with that. But here we make the simplest assumption that that function that generates the data set is the linear function of the features, right? That the simplest assumption we make about the data set. And we see how that model that we have learned performs on the training data set. If that doesn't perform well on the training data set, then we go to higher polynomials function as well. We try to fit 2-degree polynomial or 3-degree polynomial depending upon how those performs on the training data set, right? And that's the simplest assumption we have seen. And here we make assumption that every data points in the training data set has some noise associated with that, and that noise comes from the Gaussian distribution with mean. Okay, so here epsilon follows normal with mean 0 and some variance sigma square, right? And that's a reasonable assumption as well, because we assume that on an average the noise associated with each and every data point is 0, and with some variance associated with that. So if variance is high, it means that some point may have high positive error and some point may have less, negative error, and that will cancel it out. And so high error means that some may have high positive error, may have high negative error, and lesser variance means that there's some less positive error and negative error, and that will cancel out to on an average errors to be zero, right? And that leads to assumption that the by I given xi, the labels follows normal distribution with this parameter, and we don't know these parameters. We estimated those parameters using some techniques, and we know the techniques as well, right? The maximum likelihood estimation techniques. Okay, so since these W's are random variables, right? Because this randomness coming from the byes, because those byes are coming from some function f that we don't know. These are coming from some distribution, and we have access to some uh, instances of those distributions, right? Some data points that are coming from those distributions. So these by is actually are random variables, and because those by labels are random variables, the randomness comes into this model, and that's why we are calling W as a random variables. And so, and we estimated our W using the ML estimator, and these leads to the same problem that we have done using using the square loss error function, right? So till this
May
point,
I ask a
any
question here?
questions? Yes, sir.
Yeah, I have a question. The error part is okay, but why do we call W as a random variable? Because given the x's and since we are trying to predict y, there is
Mm.
perhaps one or two sets of x's that will contribute to, sets of W that will contribute to y. Why do we call W as a random variable then? Because of any particular reason?
Okay, so you can think this as a, like, assume that there's some distribution X where the training data set is coming. Let's call that training data set D, right? The data set is coming
Mhm.
from some real distribution X, right? We don't know. Let's assume now you have two training data set. Let's call them D1 and D2, right? Both are
Mhm.
coming from X, the same distribution X, and we and or say those data points have this one function f of x which generates those data points, right? Let's assume you have 500 data points here, 500 data points in the second training data set. Now you train your linear regression model for this training data set and this training data sets, right? Training means, or learning means, you have come up with some w vector here, some w vector here, right? So what do you think about those W vectors? Are they gonna be same or some different, or they will vary, or they may approximate better? What do you think about those weight vectors?
It depends on the data set itself, isn't it? Like
Yeah, yeah,
if
exactly. So they depend upon the data set, right? So that's
yeah,
where the randomness comes in, because we
okay,
never know which functions are generating those. We are trying to approximate that function by using these techniques, that regression model, right? So
okay,
that's where the randomness comes into, and that's where our next problem is, because we never know both is the true function. We have come up with some model, some functions, linear functions or polynomial functions. We are trying to find out how close that model or that function is to the true function that we need to answer now.
okay,
Okay, is
yeah,
right?
yeah.
Sir, how do we get the true function?
We never know that true function. We are trying to approximate that function using our training data set. The only thing that we know that the training data set, there is some function f that generates the training data set, or there is some distribution from which our training data set comes. That's all we need,
Okay, okay,
right?
okay.
Okay, so any more questions?
Sorry, I have one basic question. In linear regression, when we're looking at the probabilistic view,
Hmm?
what is the advantage of it? Because
It's
earlier,
just a different point of view of the same problem. We have come up with a model using some method, like we have said this is our error function, and for error function we try to optimize and get some w's using some optimization procedure, right? Some normal methods or gradient methods. The same thing comes up with the probabilistic view as well, just a different point of view for the same problem.
okay, so this is just an alternative view. There is no
Alternative
major.
view for
Okay, okay.
Sir, if we don't know the true W, then how do we know how close is our
yeah,
estimate?
so that we will see here, right?
Okay,
So that's where your knowledge of statistics will come into picture, right? So you
okay.
have all studied. I assume you all have studied the random variables, their estimation problem, maximum likelihood estimate, and how to check the performance of the estimators, right? You must have come across these bias variance and maximum mean
Yes,
expected
sir.
error, right? In the
Yes, sir.
stats courses. So that's knowledge you have to apply it now. So W is a random variable that all of you must agree now, right? W is a random variable, and the randomness comes from the labels, right? Those data sets. Okay. Since W is a random variable, this is a, and now we are trying to find out W parameters we estimated using MLE, right? And we got W star as X transpose inverse, xy, right? That's what we got. So this is our estimator. Now we have to answer how good this estimator is, right? So this is the estimator. So what are the different ways to check the goodness of or the performance of a estimator? That I already answered. There's some different measures like bias variance. We check the bias, what is the bias, what is the variance, and what is the mean squared error, right? So I'm calling that WML. That this is nothing but your XX transpose inverse XY. This is your one estimator for different training data set. This WML will be a different thing. So it's a random variable, and we use this as estimated for our the true W. This is our true W that we don't know, right? So what is the mean squared error? MSE you must have seen for any random for any estimator, let's say theta cap for the parameter theta. This is the estimator for the theta, and this theta is coming from some this is the parameter for some distribution x. Okay, right? So what is the MSE for this parameter, this estimator? How do you define that? How do you define the estimate?
Variance plus bias square.
Yeah, so or you can say bias plus variance, bias square plus variance, or and another term you can call it as, you can define it as expectation of how far your how this varying, right? Distance of, or say distance of the estimator from the true value. So the expectation of that is called your MSE. And if you expand this, you can show that this is nothing but the bias square plus variance square, right? So if MSE is high, it means that some one of these your estimator is suffering from one of these issues. Either the variance is high or bias is high, or maybe the case that both are high. But there's always there is some trade-off between bias and variance. So if MS is high, you can say that one your model or your estimator is suffering from one of these issues, right? So in our case, we define we call W. This is our estimator for your true W. So what will be the mean squared error in this case? Is this is your estimator, this is your true W. So the distance of that and how that varies for different W's, right? So this is expected on an average value of that, the expectation of that. That's how you define your MSE. And if you solve this, you use distance function and this xx transpose xy. You see that this expectation is nothing but sigma square trace of xx transpose inverse. So this is sigma square. Remember that we assume the variance of the noise, and this xx transpose you already have the trace of that, right? Xx transpose inverse. So I didn't do the proof, but I have to check how this comes up. But for now, assume that this expectation value of these things is this sigma square of trace of these things, right? So this is the mean square error for this estimator. Now, so this is the one way to check how your estimator is. You have to check this error. If this error comes out to be higher, then you can say that this estimator is suffering from either the bias problem or the variance problem, right? That we have to solve. Okay. So one more thing here is that, yeah. So both the terms logies again intuitively says that this will affect your performance of the model, because if variance is high, it means that there is high variance in the noise. High variance in the noise, and that will confuse your data set, your estimate. And XX transpose is something covariance like matrix, right? So if you normalize it by n, then it becomes a covariance matrix. But this is a covariance matrix and inverse of that, and I'm taking the trace of that. It means it takes accounts of the features in some sense, some manner, right? So these two terminologies are affecting the performance of the model, the measure of that, right? Okay. So yeah.
So this WML would get closer to the true value when the sample size is large, right? Because that's what we studied in like stats before. For an estimator, it would
Yeah,
be,
so size, we are not considering size here. Yeah, that is correct point. So it depends upon what estimator you are choosing. So that point depends if your estimator has sample size in it. Like if we for general case, if I assume that you are making okay, so you are making estimation for mean and mean mu for some that is coming from some distribution, and let's say my one estimator is just the first sample, right? So this estimator is not affected by your sample size. If I take estimator as the sample mean, sample mean as one estimator, then in that case you can call it that the sample size will affect. Larger the sample size, the better the estimator. In that case, you can call it. But in this scenario, if you see here, there's nothing like sample size in this case, right? We didn't consider the sample size in our data set, in our estimator. So we cannot conclude that the larger the data set, better the estimator. That we cannot conclude. Actually, it depends upon the complexity of your model. The complexity means if you've chosen simplest linear regression model, if you have gone for polynomial degree, for higher degree, so that complexity will keep on increasing. So it will depend upon complexity of model as well, how good your estimator is.
Sir,
Okay.
won't the sample size affect sigma square in some way? I'm saying, will the noise be smaller if you take a larger
No.
sample size?
This is the variance of that noise.
Yeah, I'm
So
saying,
it's a constant.
will the noise inherently be smaller if we take a large sample size? We don't know. We can't say.
No, it's a constant.
Okay. Here you're treating it as a constant. Okay.
Okay. So that we cannot conclude directly that larger the data set, or better is the estimator. That we cannot say. Okay. So there's different parameter that will affect your model. One of those like which degree you have chosen for the polynomial regressors. Okay. Or different like how optimizations you have chosen, like learning rate and everything that will affect your model.
No, but then, sir, how do we define this true value of W? Like, how do we think about it?
That we don't know, right? We never know what is the true function, what is the true distribution.
Okay, because in stats 2, we such true values were something which we got from the distribution itself. So,
but if you have the true value, but
distribution.
if you have the true value, then what is the logic of estimating those?
No, thing is that what we got WML, that WML is something which we got from the sample, the data set which we collected, right? And the W, the true value, is from the underlying distribution itself.
Yeah, that we don't know, right? That we have estimated as W, and we are calling that as WL.
Okay, so yeah. So that W, the true value W, is actually the W star, the optimum value of W for the data set having infinite values, right?
Not infinite. It's just you cannot call it infinite. I mean, yeah, infinite is. I'm not sure whether it's the right things to say, but just think as some function is, you have some function like say you have y equal to sine of x. You have y equal to sine of x, that is generating your data set, right? So some noise is coming out to that data set, and you have access to some only few training data sets, right? And think like that, you don't know what function is generating. Here I'm just giving you example, right? So this is the function we are trying to approximate, but here we don't have access what that function is. It can be anything.
So
Right?
even in stats 2 surveys, we say that because of the law of large numbers, with basically it's like saying if we extract WML enough number of times, then it will approach the mean, right? And the variance. So that's even there. A lot of times you don't know the population mean. You just assume that the population mean is something, and then you say
that's because we increase the sample size, right?
Correct.
But here the W as said the sample size.
No. Sample size, nahi. Udhar bhi you don't increase the sample size. There the meaning of expectation is if you do the experiment enough number of times, you will converge to the mean, right? Even here, ML you do the ML estimation not just once. You bootstrap and do it many times, right? And then you say that it is likely to. So this is a theoretical construct, right? It is likely to converge to the mean, and the error difference will be so on and so forth. Even there, you don't increase the sample size. You do it as what is the meaning of expectation?
Expectation is the averaging, right? The average of the random variable.
Yeah, no, you're averaging to convey a meaning. Expectation is expectation of getting a heads. If I say I toss the coin, expectation of getting the heads is 0.5. What does that mean?
That means I can like in the next toss, I can expect my the chances of getting
Yeah.
hits.
So you
is
arrive
like
at, yeah. So you arrive at that because if you do the if you do the experiment enough number of times, in the long run, you will get 0.5. That's what it means.
okay. Okay,
Even
so
even
here also,
here, what it's saying is if you do this experiment enough number of times, you will, your WML, if it's an unbiased estimator, your WML will converge to the W of the population or whatever is the true W.
okay, okay, okay.
That's the way.
Thanks. Okay,
That's
I
the
think
way
I
to
got
do
it.
it.
Yeah. So if we do it like 1,000 times, we collect the same data of like same size, let's say, of multiple number of times. The larger the number of times we collect, the more closer it would get to the
Correct.
original value.
Correct. So
Yes.
you see, inherently, most commercial softwares have that ability saying how many times should I, like how many times should you iterate, right? Or how many times. The basic concept of epochs is that you keep repeating it multiple number of times so that you converge to, you take an average and that average will be a true representative of the W, right? So you have that inbuilt in all the softwares.
Okay. Okay. Thank you.
I hope I'm right, sir. I just shared whatever I could understand.
So,
Yeah, that's all.
yeah, okay. I actually missed what you said in between, but the point was that if you have the only thing that Sarvesh was asking is sample size will affect how good your estimator is, right? Is that right?
No, that
No,
also. And my main doubt was that how can we think about this W? Like, how do we even approach this value of W?
what is this W minus WML? What does that mean? What is the
W,
expectation
the
there
true value.
mean? That
Yes,
was the
in
question.
terms of WML.
Yeah,
Yes.
Okay,
So
so that's if because we don't know what W is, that's why we are estimating it, right? If we have W
yeah, yeah,
itself, then why we
yeah.
will
So
estimate that?
correct, sir. So
no,
that's
no.
correct.
But
So
as
that's
Vasu sir explained, like if we collect this set of data multiple number of times, and for each data set we calculate this WML and take the average.
Hmm.
So larger the number of data set we take, and so the
larger the
average.
data, not larger the data set, larger, more number of times we repeat the experiment. It
Hmm.
could be the same data set, right? We just keep on doing ML estimation more and more times, then it will converge to the mean. That's what expectation means.
Yeah, so it's a particular case when you are taking a sample mean as your estimator for your mean, right?
Correct,
So
sir. Sir, I'm just giving the idea of what
one
this
idea, yeah,
expectation.
yeah. So in
Yeah,
that
just giving
context,
an
correct.
idea
It's
of
completely
what this
correct.
expectation means, right? So
Yeah.
basically, it means, let's say the data set is X, right? It's D by N matrix. It's given.
Yeah.
It's a feature matrix, right? I estimate the ML multiple times, right?
Yeah.
In the long run, the idea is in the long run, it will converge to the true W.
Yeah, that is correct. That is correct. In that context, completely right.
Okay, yes, that only I wanted to. Yes,
Okay.
thank you.
Okay, so what we were discussing, we are saying that this is the MSE for your WML, right? Now, and we have seen that this expression sigma square trace of x transpose inverse. Now, these two terms will affect your MSE, so this is a constant. We cannot handle this, but what we can handle is this term, right? X trace of x transpose inverse, because this is one of our estimator, and that's why this comes in. And what let's assume your lambda 1 up to lambda t are the estimator. Sorry, not estimator. Lambda 1 to lambda t are your eigenvalues for xx transpose. So what will be the eigenvalues of xx transpose inverse? What will be the eigenvalues for xx transpose
It
inverse?
is just the inverse of the.
Right? So 1 upon lambda i's will be the eigenvalues of x's transpose inverse, and so then ms will become summation over 1 upon lambda i's, right? So this is your MSE for the this is the MSE for the WML, right? Now what we can do next, since if that is a constant, sigma square is a constant, but what we can handle is this lambda i's, right? So if the larger the lambdas, MSE will be smaller, and if the lambda values are smaller, your MSE gonna be higher values. So that we have to handle. So if we make sure that these eigen values are higher, then MSE gonna be smaller, right? And that's our target. We want the MSE for the estimator to be low. So what we can do, rather than using estimator as access transpose, rather than using this as an estimator, my estimator was access transpose inverse XY. What I will do, I will take this as my estimator. By taking this as estimator, what I have done, I added eigenvalues, because this is my that matrix, right? Access transpose plus lambda I inverse. So now eigenvalues will become lambda 1 plus lambda, right? For every for one, right? So this is the first eigenvalue. Second will be lambda 2 plus lambda, and similarly lambda I plus lambda will be my ith eigenvalues. And so and lambda I'm taking as a positive quantity. So I've added something into this, right? And since I've added something, my eigenvalues have become larger in values, and and so the MSE will look something like this. Now this, since I've increased my values of the lambda i's, this MSE will decrease down, right? That's what our target is. So it says that if I choose this my as an estimator rather than this thing, this my MSE will lower down, right? So why not to choose this as an estimator? So we have chosen this as an estimator, but this comes with some cost, right? Because this we have assumed that we come across this and we saying that this actually minimizes your training loss, right? But this we cannot say, because this WML will obviously will have higher loss for the training data set than that of WML, because this is our design, right? Because we assume that this particular W will give me the minimum loss. But so from that we can say that this W actually will not give me the minimum loss. Your loss will be higher than that minimum loss. But what you can ensure is that your MSE for your estimator will be low in this case, right?
Can I ask a question, a very fundamental one?
Yeah.
Lambdas belonging to XX transpose, I understand. But plus lambda I, what is that lambda and what is the basis for adding it?
So our MSE was sigma square summation over 1 upon lambda I, right?
Correct.
So we have to ensure that this eigenvalues should be smaller. So it
Yes.
should be larger. Should be larger, because we want MSE to be lower, right?
Lower, yeah.
So if the lambda 1, lambda 2, lambda i's are the eigenvalues of access transpose, what will be the eigenvalues of this thing?
Yeah, that part I get it. Like when you ask me about that, then I'll say lambda I plus lambda at the denominator. But
Yeah.
how do I know what that lambda should be?
Yeah, so that depends upon. So here this lambda is a hyperparameter, and how to choose that that lambda that comes that we do using cross validation techniques, and we will discuss that how to choose it, values of lambda.
Okay.
Okay, so till this point, you got the idea, right? We have chosen a new estimator, and by choosing those estimator, we have ensured that your MSE is decreased down, but with some cost. I mean, the training loss may be higher in that case, and probably will be higher, right, than the linear regression loss. So till this point,
Uh,
any doubt?
yes, these eigenvalues,
Hmm?
that is the summation of these eigenvalues to get the trace. Why are we doing 1 by lambda I initially? Not this, but here,
This
why
thing.
was it 1 by
So
lambda I?
this is the trace of access transpose inverse, right? So
Oh,
remember
the inverse would have
remember
instead
the
of 1.
property trace. Trace is actually sum of eigenvalues,
Right,
right?
right.
So this you must have seen.
Yes.
So eigenvalues of access transpose is lambda I. So eigenvalues of access transpose inverse will be 1 of lambda I. So trace gonna be sum over 1 of lambda I.
All right. Thank you.
Okay. Okay. So now the different ways of looking at this estimator as doing the Bayesian estimation. So what we do in the Bayesian estimation? Now we have so let's let's quickly recap what Bayesian estimation is. Let's assume your parameter is theta that we don't know, and that is coming from the distribution X. So how to estimate that parameter using Bayesian estimation? So can anyone please explain how to do Bayesian estimation?
So we take a prior and then we modify it based on the estimate.
Yeah, of course. So here we assume that that parameter is not a constant, right? In the frequencies estimation like MLE, we assume that theta is unknown but a constant quantity, right? Here we assume that theta itself has a random variable, right? And it's unknown, but it is a random variable that we assume in the basic modeling. Now we assume some prior for the theta. Let's assume capital theta is the prior for that, and this is some prior for that, and we uh, collect some observations, we collect some samples, and we find the likelihood that sample. Using that likelihood and prior knowledge, we update on prior knowledge, and we find the posterior of that, and we update our belief about the theta. That's how we goes in the Bayesian model, right? So for the same problem we apply here, our data again the same thing. We assume that the data set is coming from normal. Data set is the labels given features follows normal distributions with varying sigma square, but here for simplicity it's taken as one, and the mean is W transpose X. The same problem here, our task is to estimate these W's. So in the basic modeling, what we assume W as a parameter, W as a W as a random variable, and we assume the prior for the W as in Gaussian distribution. So why we choose Gaussian? One reasoning of that choosing Gaussian is because normal is conjugate prior to normal, right? So we choose normal, and why we choose zero mean for W, that we will answer later. But for now, assume that we choose zero mean for the prior of W's and with some variance. So this is your covariance now. So gamma square will come from R d cross D. So it's covariance matrix for W, right? So this is the prior for W. Now what we do, we will collect some data set. So data set is our training data set. So
why are we multiplying with I here?
It's an identity matrix. It's just identity matrix, right? So we'll keep all the covariances, like all the variance of the features, also the W vectors in that diagonal matrix, only diagonal elements as a diagonal matrix. So that's how we define a covariance matrix.
Sir, can you repeat again?
Sorry?
Can you repeat again what you said about?
So if in the covariance matrix, you think covariance matrix as an square matrix with all the entries only at the diagonal, all other entries as zero. So this is how you define a covariance matrix, right? All others you assume that your weight vectors, the features are not related to each other. That's why we assume it to be zero and only take the entries only at the diagonals.
Sir, basically the diagonal entries are the variance of each of the feature, correct?
Features.
Just to make it the variance, right? We are multiplying it with I.
Yeah, for the identity.
Yeah, and sir, why are we assuming that the rest of them are zero? Because there is no like covariance between.
Yeah, we'll answer that. Why we choose zero prior for the W vector? We'll answer that, right?
No, the mean is fine, sir. The mean I understood. I'm talking about the covariance matrix also. Why are we assuming that the rest of the values are zero? We are assuming there is no variance, no covariance between features.
Yeah, that's the initial assumption, right? We assume that all the features are uncorrelated to each other. Right?
Yeah, which is in real life never true, but that's okay.
That's why this sigma square need not to be an that scalar matrix, or that's why we multiply it with the identity matrix. So this becomes sort of covariance like matrix, right? This sigma square actually need not to be one with all the entries at diagonal. It can be.
So we can replace this with covariance matrix, proper covariance.
Matrix. Yes.
Okay. Thank you.
Okay. Okay, so we have the prior for W, now we have the observation. So what is the next task? You will find the likelihood. Likelihood means that what is the probability of the sample that you have seen given the parameter w, right? And we update our knowledge. Uh, we call that as a posterior. Posterior is proportional to likelihood times prior. There's evidence as well, but we avoid evidence because it's common in all the things, right? So we just take the proportionality constant here, and so likelihood gonna be what? It's the probability of observation that you have seen given the weight vector, and the prior is what that you have already assumed to be normal. If you apply this, right, because you know the distribution of this by I of xi is not again normal with w transpose xi and 1, and prior we already know, right? So if we apply this, you will get, if just do the mathematics here, and you will get this expression. So this is how your posterior looks like, right? So what do you think is what distribution this is?
Normal, right?
Normal again, right? Because, or you can directly say that because you have prior as a normal distribution and the distribution again normal. So these are the conjugate prior. Conjugate prior means that the posterior again gonna be your normal distribution. So again, this is a normal distribution, and what we are finding as the mod of this. So mod is our estimator in this case, which is called maximum a priori estimate. Okay, so this is nothing but the mod of this distributions, right? So we take the maximum of this thing, right? So again, we have seen this kind of problem. This is again a optimization problem. So rather than maximize this thing, you can even write as the minimizing this thing. So this is again come to the optimization problem, right?
Sir, I have one question here, sir. Why are we? I know it's a normal distribution, so mean and mode will be the same. Mean, median, mode will be the same. But why are we taking median mode here, sir? Why not mean?
Okay, why we choose mode is that I'm also not sure, but that's how you define your maximum a priori estimate.
I know, but why suddenly maximum a priori estimate is what I'm wondering. I tried to read everywhere. Everywhere it says it may, but I don't know why they are choosing may in this particular situation.
Okay. Okay. One is that leads to your regularization problem. That particular point of view leads to your that regularization problem. Another estimate is like you mentioned, like mean or other thing. Not sure whether how they will perform, but in this case, MAP is taken as your estimator. I'm not sure
Could
why
it be
exactly.
because of the maximum number of points lying on the mode, or?
No, but by that logic, Ravi, everywhere we should do MAP only. Why do we take mean?
True. Good question.
Yeah, but for normal mean median mode is the same.
Will
But
coincide, right?
yeah, but
Yeah.
here we have an additional factor, which regularizer factor. So I don't know why there has to be a specific reason as to why we are taking MAP here and
No,
not.
no, no. Even though there is some factor, but it don't affect your distribution. It is again gonna be your normal distribution.
Correct, correct. Then why not just call it posterior mean? Why MAP?
Okay,
Uh,
whatever you call it, right? Whatever you call it, whether it's a mod or mean, it's gonna be same, right? In this case, in this particular case.
that's true, sir, but that's still not that's still not like answer my doubt. I'll try and figure out, but if you get to know, please let us know. Why are we
You check that,
specifically?
but my reasoning says that both are gonna be same. You go using any path, you're gonna reach at the same quantity, same point.
Correct, correct, correct. But I'm saying that why not call it mean only? Why call it MAP and confuse? Because everywhere we use mean. So if they're suddenly calling it this, there is some reason for it, is my guess.
Okay, okay. I'll try to read it out. If I get something,
Yeah, I tried to
I'll
wherever I seen it says MAP. I'll also try and read. I will let you know if I find something.
okay. Yeah, okay. Okay, so we have come again with this optimization problem that we can easily solve. Again, it's a nice function, quadratic function in W, right? So what are the ways to solve this optimization problem? We have seen two methods, right? One is take the gradient and set it to 0, or take the gradient methods like start with some random point and then move into the direction of the minima, right? So what is the gradient? What will be the gradient for this function? This is again the loss function, right? This is the squared loss function with some terms added to this. So you can easily see that the gradient gonna be x transpose w minus xy, and this gradient gonna be w by gamma square. So generally this 1 upon gamma square is replaced by some another constant which is called lambda. This is called this is called regularization parameter. Okay, so this is one hyperparameter in this case. How to choose this lambda? We'll talk about that. Okay, so this is your gradient of that. If you set equal to 0, you will get your answer. This is you get your optimal value. So this is how your optimal W will look like, and that we have seen using our that's how we design your. Remember, we have designed in the same fashion, right? Yes.
Sir, one clarification. This lambda and the eigenvalues have no link, right? They're not connected.
Lambda and
The
no.
lambda and the eigenvalues are
There
not
is no
connected.
link. There is no link in the eigenvalue.
I just wanted to clarify. That's all. Thanks.
Right? So that's how we design your new estimator, right? Now you can think this is a different estimator. Now this trending loss of for this again gonna be higher than what W star achieved, right? But it makes sure that your MSE gonna be lesser in this for this particular W, right? Okay.
So in this case,
So,
gamma square is what exactly is gamma square?
gamma square again that we have seen, right? Gamma square is the covariance matrix.
Correct. So, okay.
Right? So this is actually replaced by some another concept which is lambda W square, right? So this particular, this is the square loss, and this is called regularizer, right? So our task is to minimize this loss, right? So minimize means this you are actually minimizing the scale loss, and you are also making sure that the magnitude of W is not becomes very large, because if the magnitude of W becomes large, this whole quantity will become large, and our task is to minimize this. So along with minimizing scale loss, you are making sure that your W's are close to 0, or say your magnitude of W is very low, right? And, sir also gives one example, right? So this actually is what happens. So in this manner, what we can do, we try to stabilize our model. Right? Stabilize means that your MSE is gonna be less in this case, and it also reduce the multicollinearity. What is multicollinearity? Have you come across this term before?
Yeah, like for example, the covariance matrix will not be just a diagonal matrix. It will have values all around.
Yeah, for the features, right? So
Yeah.
multicollinearity means how the different features have correlations. So if there's lots of there's correlation between different features, then this problem may be reduced by multicollinearity. And how sir has given example, like you assume you have some features x1, features x2 feature, and some other feature x3, and the feature is related to x2 or x1, something like x2 plus x1, and then we have some labels, and now we are learning our model using these three features. Now this is our redundant feature, because if you learn some weight vector W3 for X3, it again can be write as some features of X2 and X1, and this is some redundancy we have added into that model. So such kind of redundancy can be reduced by reducing the weight, reducing the magnitude of weight vector. So reducing means that we are shrinking weight vectors to 0, right? And shrinking 0 means that we are not giving higher weightage to some of the features, and we are not giving, so the weight vector base reduces to 0. It means that those features are actually redundant features in our models, right? So that's how we reduce our issues of correlations of different features by using the regularization terms, right?
So if there are multiple values that are possible, then we compute the loss for each set of values and see which one is the least, and then take it, is it?
Yeah, we'll take it that way. Because it makes sure that taking weight vectors which are closer to 0 makes sure that some of the features are not affecting your model, right?
Okay.
So those features
Again,
you
weight
can think as the redundant features in your model.
and weight vector square, when you say it is the vector, I mean the sum of the squares of the weights.
Yeah, this is second norm, L2 norm.
L to norm, okay. And you take half of it, okay. Okay.
Okay, so why did we choose 0 means? So it 0 means it makes sure that the regression coefficient becomes small and centered around zeros. So it again reduces your impact of multicollinearity. And when we choose zero mean for the prior for W, it your the posterior mean again is not affected. It's again centered around mean, and it means that those also your weight vectors you are trying to shrink towards zero, right? So that's why we choose W's to be mean centered around zeros. So that is why we choose zero means for the prior for W. Okay. Okay. So that
Sorry,
is
one
all
second.
about the
It encourages the regression curve. Can you repeat
yes.
that part? Sorry, the one that you just why we choose mean zero.
Mean zeros because at last what we want to those W vector to be centered around zeros, right? So that is
Correct.
one idea while choosing your mean to be zero for the prior W.
But in reality, W, I mean, the zero need not be the mean, right? So we center the data. That's the reason why. I mean, is that what?
No,
What
we
it is?
don't center the data. We don't center the data. We actually want W's to be closer to zero. That's why we choose mean to be zero for the prior.
Okay. But the posterior may not end up with a mean prior to, I mean, mean close to zero, correct?
No, that need not to be.
Okay.
Okay, so now we'll try to see the locations of these two estimator geometrically. So now this was our actual optimization problem where we are trying to minimizing this thing, right? So can this optimization problem can this problem be written like this? And claiming that these two optimization problem are equivalent. Have you shown such kind of problems in your optimization? This is your objective function and this is your constraint function. Have you seen the birds like Lagrangian?
Yeah, we've seen it in MLF.
Right? So you must have solved such optimization problem. Right? This is your objective function and this is your constraint. How do you solve such problems?
So you one is this Lagrangian, the other one is KKT method.
Yeah, so that is high, but this here is a convex function and is only one is constraint to that. That is not very hard to solve. So we can go from the Lagrangian method, right? So what is the Lagrangian in this case? This one is the Lagrangian, right? So these two are equivalent formulations, right? Or one way to think is like that you are actually minimizing the square loss, right? So you are minimizing the square loss and you are making sure that your W's are not getting bigger or closer to W's, or with subject to that your magnitude is not getting very high, right? So one way to think is like that. You just do writing the same thing in the different manner, right? So these two are the equivalent thing. Now, so for simplicity, I'm assuming W to be the two-dimensional vector. So there are only two features. I'm assuming W as a W1 and W2. This is the two-dimensional vector now. So what this constraint will look like? So norm of W gonna be W1 square plus W2 square less than theta. What this equation is? This is your circle, right?
Interior of a circle, right?
Right. So this is your W1, this is your W2. So if you draw this is going to be your circle around, which is centered around 0, 0. So this is your circle. You want this to be less than theta. It means that you are looking theta inside this circle, right?
So
So
it's less than equal to, so it would also include the edge, right?
Yeah, include the S. You are also considering this as well. This this right very that you. Okay, so you are looking your WMAP to be inside this, right? And let's assume your WML lies somewhere here, right? This is your WML. So what is WML? By design, we know that WML actually suffers the minimum trading loss, right? That's how we call it WML. WML we remember we obtain using solving the optimization problem, which actually minimizes the square loss, right? So this WML actually minimizes the training loss. So you choose any W other than WML, you will say that loss for that particular W gonna be higher than this particular loss, right? That we say that. So WMAP again will incur higher loss than WML. Let's assume those W actually is that loss for that W is higher by amount C from the WML, right? So this is the loss that WML suffers, and this is the loss that your W suffers, that WML that you are finding the locations, right? And this is loss is higher from WML, right, by some amount C. So if you solve these equations, you will get such kind of equation, and this is equations of the ellipse, okay, which is centered around this WML, right? So what you are doing, you are finding your W from the ellipses which are centered, whose center is this WML, right? So you are looking your WML from here, and we have already seen you are looking your W inside this circle only, right? And if you go far away from your WML, your loss will be, this is your WML, right? So if you go far away from this WML, you will suffer more loss. So what you will do, you will keep where you will choose that W which hits this surface, right? Because you're choosing inside this, and this gonna be at the surface of some ellipse of around WML, right? So this point actually gonna be your WMAP, right? Got the idea? Why I call?
Can you just scroll up?
Sorry.
Scroll up. Okay. Yeah. Now, sir, why you said like loss? We are like looking for loss more than
because
WML.
this WML will suffer the minimum loss, right? What we call WML is one. We obtained using this problem, right? This R min norm of X transpose W minus Y, right? So we obtained using solving this problem, right? And what is this thing? This is the training loss, right? And since we obtained WML obtained using solution of this thing, it means that this particular W suffers the minimum training loss, and any other W will incur more or at max similar to this loss, right? Not like that W cannot incur less error than this one.
Okay.
Okay.
So what's an MLP?
Sorry.
Why did you say MLP? Where is it P comes? I'm not getting the P. No, in the graph, the circles.
MLP, MAP.
Yeah.
This is maximum a priori.
Okay.
Maximum a priori estimate. Okay. Okay. So any doubt till this point?
Yeah. Can we go and see those equations that you wrote up there for the optimization, please?
This one.
Yeah. So
What's your doubt here?
just trying to understand. So I'm computing the same function, just assuming that a W is not exactly equal to WML. And
Yeah, WMS. So this particular loss gonna be more than this loss, right?
Yeah.
This is the loss incurred by the WML. So let's say this loss is more by some amount.
Why do we say it is less? Because we are assuming C on that side, or is it normally itself that W will be more than the loss will be more than
this W will incur more loss, right? Than WML. That point is clear or not?
I think that is where I'm stuck.
So how we find WML?
Maximum likelihood. So
no. So WML actually we found using this optimization problem, where we call this is we try to minimize this thing, right?
Yeah.
So we actually look that W which minimize these things. It means that this WML actually is the W which has the minimum training loss. Right?
Yes.
So any other W other than WML will incur more loss than WML. Okay.
Yes.
So let's assume for that W that we are looking for is more than by some amount C for that
Okay.
loss, right? And we solve this
Okay.
equation, we get this particular equation, and this is an ellipse in two-dimensional space if you take W as a two-dimensional vector, right? Okay. So that's how we get the position of WMAP. So it's gonna be on the circumference of this set. Right. So this particular formulation is called ridge regression. Okay. So here we haven't discussed how to find lambda. We'll discuss in the last part of this session. Okay. So any other doubt till this point? If not, we can move to the next regularization, which is L1 regularization. It's just the same formulation we replaced the L2 norm by the L1 norm, right? So here, remember it was a norm of W square, which was the L2 norm. Here we have taken the absolute norm, which is L1 norm here. The same thing, squared loss, and this is the regularizer, right? So again, the same thing can be
Sir,
rewrite.
L1 norm here is the Manhattan distance.
Yeah, so Manhattan distance is actually here I'm taking norm for vector, so it is defined as let's say W1 plus mod of W2 plus 2 mod of W3. That's how you
Yes,
define
okay.
it.
Okay, thanks.
Right? Right. So this particular formulation can be rewrite as in this thing. So same thing here. So if you solve this, what is this? This is something like that W1 plus mod of W2 is less than or equal to theta. So what are those equations? How this region look like? How this particular region look like? It's just like W1 plus W2
It's
is
a
less than
diamond,
theta.
right?
Yeah, some kind of a square, right? This is square, right? So now you are looking your W inside this, right? Inside this, and again those will coming from this is your WMA, so those will lie on the ellipse which is centered around this thing. So where this will hit will be your solutions. It most likely to hit on this corners, right? So it's because the optimization problem says that your corners will most likely to give you the solution of the optimization problem. And even if you think this is gonna be, if you keep on finding the ellipses, most likely it's not that always it will hit the corners, but most likely that the solution will like on the corner. So if you corner, it means that your weight vector has become zero. So if it hit this one, your W2 becomes zero, and if it this one, it becomes W1 becomes zero. So choosing L1 norms has that's why we choose L1 norm. L1 norms make sure that your features have become exactly zeros, right? Or say the features, not the features, the weight vector has become zeros. So your weight vectors are more sparse in the case of the lasso, right? But in the case of risk, that has come to close to zero, but not exactly zero, right? But in the case of lasso, there's most chances that your weight will become zero, right? And uh, what is the use of that? You can say that if some weight becomes zero, it means that you have reduced that weight from that features from your model, right? You are not learning that features itself. So that's how you reduce that redundancy from the model completely. Okay, so that's why Lasso helps to reduce your that redundancy in the model, right? So more sparse means that more bit vectors will become zero in the case of lasso. Again, here we have to see how this lambda to find. Okay, the same formulation, but with the same up. But here, if you see this formulation here, this optimization problem you have to solve. So what is the problem to solve this optimization? Can we solve using gradient? Is this function differentiable?
No. It's
right?
not.
So this function is not differentiable at some points, right? So this is the issue with this optimization problem, and there is no closed form solution for this, like, because no closed form solution for this Lasso regression. So how to do that? We are not covered in this part, but some idea like this. So we find the sum gradient for the loss function. So assume this is your function, some f of x. It's not the loss function, but some function. So what is the subgradient? So this function is not differentiable at this point, right? So we define some gradient, subgradient at this point, and this is just a vector. Let's be calling this z. We call a vector z to be subgradient of the function f at x, right? So we call this vector. This is a vector. We call this vector is subgradient at x at this point 0. In this particular case, at 0 for the function f when this condition holds, right? For f of z is greater than f of x plus g transpose z minus x. So what this condition says that this function always gonna be up on the upper side for this function, this vector, right? So if it happens, then we call that vector to be subgradient at that point. So there may be different subgradient for this particular point. So this will be a subgradient. Again, this particular line again, this particular vector again gonna be subgradient, right? So for any points, if we define subgradient here, if there exists only one subgradient, then we call that the point is differentiable, right? So the function was not differentiable at this point. We define the subgradient, and there may be more than one subgradient at that point. Okay. Okay. So this equation says that you take any points, and your curve function, your function value is gonna be more than the vector point, right? Vector at that point. Okay. Generally, this vectors actually is nothing but the slope of that vector, right? So if you think like this thing, right? So here it's one dimensional line. So slope is something like, let's say 45 degree, or say so 1045 gonna be some. Let's say slope is 1/2 for this. So in this case, g gonna be your 1/2, right? So if you take any point here, so let's say, so it will look like something like the f of z is greater than f of x is mod of x, right? Plus 1/2. So transpose of that vector. In this case is one dimensional, but in a real case, this is gonna be the dimensional vector, right? So that you take the transpose of that, and it becomes z minus x, right? So this become mod of z is greater than mod of x, and plus. So this equations says that your function value is always, so this says that this function value is always going greater than this thing, something like this. So so that. So I've taken some random number, but in general, tells that it's gonna be slope or something like that. This vector. So this some gradient methods are used to find the optimal values rather than using gradient and gradient descent method. You use subgradient if the function is not, if the loss function is not differentiable at that points, right? Okay. But we have not discussed in details about the subgradient methods. But you got the idea, right? How we can use subgradient to update your weight vectors, right? Okay. So yeah, so that's all about rigid regression and the Lasso regression. So any doubt, if you have, you can ask. Otherwise, we can discuss how you find this lambda, right? So this lambda was the
Sir,
hyperparameter.
one question, sir.
Hmm.
Let's say both MLE and your
MAP.
or no, both MLE and Ridge are giving us two options, right? Like two options for the weight vector, right?
Both MLE and Ridge, okay. Giving,
Ridge, right? Let's say giving two options each, okay? Because MLE also can give, if it's an underdetermined system, you can have multiple answers, right? If they're infinite solutions.
Okay.
Now, in these cases, while there is no regularizer in MLE, it or the regular linear regression, it will still choose the one with the lowest norm, right? Because that is what pseudo inverse does.
MLE chooses the, okay, or you are saying Ridge one, right?
No, Ridge one will anyway choose with the lowest norm. Even MLE, if I have multiple options, because it looks for pseudo inverse, it will choose the one which is the lowest norm, correct?
So in that case, it's gonna be one. If you have one fixed training data set, right? You will always get only one W.
No, I can get multiple W's depending on the training data set, right? Even for regular regression. Forget about ridge and all.
Okay, for regular regression, the simplest one that we have seen ordinary linear regression,
Correct.
you will get different W's for the same training data set.
Because if I have more than one solution for that system of linear equation, I can get multiple W's.
So in that case, what you have done, you have rerun your procedure again. You started with some random points and reached to some W1. Again, you restarted your some initialization and you reached to W2. Something like that we have done there.
No, sir. No. So, no, I was assuming that that's what pseudo inverse does. When there are multiple solutions, it will look for the one with the lowest norm.
Okay.
I just wanted to clarify that point.
Okay. I got your point.
If there is no inverse for xxt, it will look for the pseudo inverse.
Yes, pseudo inverse.
Pseudo inverse will always look for the lowest norm.
Okay. Yeah. In that case, again, you will get multiple W's. Then you will choose for one.
Both will choose the lowest norm. Okay, got it. Yeah. I just wanted to clarify that. Is that how pseudo inverse works? I wanted to clarify.
Yeah. That is right.
Got it clear. So this MAPE, if you can just MAPE versus whatever expected mean, expected versus maximum. Why are we calling it maximum? If you can just figure that out,
Sorry. Can you please come again? Last part.
The same question earlier which I asked, which is that MAP versus the mean, using mean instead of mode. What does happen and why are we choosing mode? I'm saying that one question is still pending. If you can answer that at some point, it will be helpful.
Okay. I'll try to read out. If I get some resources, I'll share that.
Sure.
Okay. So the question that remains now is how to choose that lambda. So lambda is your hyperparameter, right? So one thing, tell me, your problem was your ridge regression problem and Lasso was you have to minimize this thing, right? This is not summation. You can think as norm of x transpose w minus pi whole square minus plus lambda w square, right? This you have to minimize, right? And in the case of Lasso, you have norm 1, right? This is norm 2. Okay, so if I increase the value of lambda, what will happen to W vector? It will decrease or
increase, right?
If I increase the lambda, W vector will tends to increase, or I mean, the norm of W will tends to increase or decrease?
Decrease.
Decrease. Why decrease?
Because it's trying to keep it minimum, right? So
because we are trying to keep this minimum, right? So if we keep of increasing this, you have to make sure that this decreases, right? Similarly, if you choose lambda equal to 0, it means that no regularization, right? Or other way around also true. If you decrease lambda, your W vectors are not penalized much. Per se, they are closing to your W star that we obtain using the ML event, right? Okay, so
but you just mentioned a little earlier that W would try to keep it as close to 0 as possible, isn't it?
Yeah, so that's where the role of lambda comes into picture, right? For lesser values of lambdas, that W again gonna be close to the W star. But if you choose the higher values of lambda, then it will keep closer to zeros.
If W is already close to 0.
No, that is the prior, but we have updated your prior and we got some this estimation, right? X transpose x not x transpose x transpose plus lambda I inverse x this one, right? So this is your now estimator WMA. So that was the prior assumption. Assumption is make sure that you want your W's to be close to 0. That's why we assume W's to be 0 in that case. Okay, so how to find this lambda? We find this hyperparameter using cross-validation techniques. Not just this one, any hyperparameters is actually found using cross-validation techniques. There are a bunch of cross-validation techniques. Here we will discuss about k-fold one is out of those k-fold cross validation. So what happens in k-fold cross validation? Okay, so what you do, you have let's say you have training data set, right? So you divide your data set into two parts. One is training data set, another is test data set, and another third part is the validation set. Okay, so this is used for the learning or training your model. This is used for the evaluation part, and this is using for validation, or say the finding the best pair of best hyperparameters. Okay, so in the k-fold, what we do, let's keep aside training data set for now. This part is easy. You divide your training. You have training data set T, or called D. Now, in you divide your training data set into k folds. So if you have 1,000 data points into 1,000 data points in your training data set, you divide into k folds. Let's say 10 folds you divide. So you are doing 10 folds cross validation. So you divide into 10 folds, each with equal data points. So how many data points will there in the 10 folds? So there will be 100 data points, right? So 100 into 10 parts you divide into this. Okay, so these are your 10 folds. What you do, you use 9 folds for training and 1 for validation, right? And similarly, you keep 1 aside for the validation and use 9 for the training, right? So in this manner, you train your model 10 times, right? And for different values of lambda, you do this. For let's say for particular lambda one I've chosen this tactics, and I find out the validations loss in this case. Loss on the validation set. I train my models on the 9 folds, right? And that I use that model to find a validation loss. And I keep track of all those 10 loss. So for particular lambda one, I will get the validation loss is the average of all those 10 losses, right? Let's call this is K1. Similarly, you choose some different values of lambda 2. Again, you will do the same procedure. You will divide your data set into 10 folds. You train 10 models and you find the validation loss for those 10 models. Take the average. That will be your, again, your validation loss for the lambda 2. Again, you will do for lambda 3 for bunch of lambdas you choose, and you choose that lambda which suffers the less validation loss. That's how you will find the validation loss using k-fold validations, cross validations.
Okay,
There's
we
one.
get 10 sets of data. What do we do with the 10 sets of data? Take an average or?
So for let's say for particular lambda one, you
Yeah.
divide your data set into 10 parts. You take 9 folds together, leave 1 folds out for validation.
Yeah,
You
got it.
train your model into this 9 folds.
Yes.
You find the validation loss on the validation set.
Yeah.
Right. Again, you choose. Let's say you have chosen 10th as the validation set. In the next, you will choose 9 for the
I get the
validation
10
set.
times. 10 times I do that, and I have 10 validation sets and 10 loss.
10 losses. You take the average and you are calling as a K1. Again, you
Average
do
of the losses?
average of the losses.
Then we can't fix the lambda, right? Are we not choosing the minimum one which gives a minimum loss?
Yes. So for lambda one, I'm calling that average loss as the validation loss. Again, you will do for lambda two the same procedure.
So we choose whichever is the that particular lambda which has a minimum loss, right?
Minimum validation loss, right? Okay. So this particular technique
Sorry,
is called.
is the average or the minimum?
No. So you have K1 for the lambda one, K2 for the lambda two, right?
Yeah.
So you have tried out some, let's say lambda and n lambdas. You have K1, K2 up to Kn.
Correct.
Right. So which lambdas give the minimum validation loss? You choose that.
But K1 itself is the average of
It's
the
a
10
number,
times.
right? It's a number. At last, it's a number, right? The one which is the minimum loss is the you choose that lambda.
So, sir, we start with some lambda and we compute K1. Then we change the lambda, we compute K2, and we try a bunch of such lambdas. Let's say we try L lambdas. We have K losses, and we choose the lowest loss here. And each loss, when we are computing, we are doing it through k-fold validation. So it will be average of those whatever k-folds.
Yes.
Right. So
Yeah, right.
and we choose the lowest one. Got it. Okay.
K itself is the average for a particular
Yeah.
lambda.
Yeah, a
Yeah.
particular
For
lambda.
every lambda, there are k number of times it runs. See, I think the k thing, or whether it's epochs or k here, it's basically to make sure that we don't end up with some edge cases, and it's kind of averaged across various. It's basically like bootstrapping only, right? The same thing.
Okay. Okay.
Okay. Okay, so one extreme case for k-fold is when we choose k equal to n. I mean, every data point has one fold, right? So that is called one leave one out cross validation. Leave one out cross validation. But generally, this particular is not used. It's used when you have very less data points. Okay, generally this one is not used. Okay, so there are different techniques for the cross validation. This is the only one we have discussed. There are many that we will discuss, I think, in the probably in the practice course, not in the new practice course. There are
Sir,
many
what
techniques.
you said in leave one out.
Leave one out, we choose k equal to n. I mean, we choose n folds. N folds means in every fold you have only one training one training data point.
Okay, from every fold, we are training the model, right?
Yeah, every fold. Not every fold. We take one fold as the validation and all others as the training data points. Right?
And that repeats k number of times, right? For
K number
every
of
lambda.
times. K number of times.
Okay.
Okay. So that's how you choose your hyperparameters. Okay. So any doubts in this? If not, we are done with this particular week regularization. It was relatively very small week compared to others. I hope you got the ideas of week 6, what we are trying to do here and why we are doing this.
Sir, are we not going to have any more sessions for week 6? Yes?
We'll have one more on Tuesday, not Tuesday, Wednesday, 2 to 4. Probably we'll discuss some of the questions, open session type of questions, and then we'll discuss the programming part of week 5 and week 6 that we haven't done, right?
Sir, can you upload the programming assignment file, sir? The Jupyter notebooks.
For week 5 or 6?
Both, sir. Both are not updated.
Okay, I'll upload those. So Tuesday 2 to 4, not Tuesday, Wednesday 2 to 4, I will take one session, and I think we are done then week 5 with week 6. Right?
Okay, sir. Okay.
Fine.
Sir, please solve some problem that we can get hint that how to solve graded assignment, because in the video lecture there is no mathematical problem. There is no example.
Okay, but in the assignments again there are not much numerical questions, right? And if are there, you please come up, solve those questions in practice assignment or in the activity questions, and we can solve those in next session and open session. You can always ask those questions.
In Wednesday
Yeah,
session.
Wednesday session we can solve this.
No, Wednesday is the last date of
Or
submitting.
even if you have any doubts in any questions, you can ask. I can solve it here.
Okay, there is
Sir,
some numerical problems in graded assignment 6. Actually, solve some question, but not confident.
In week
Because,
6, is it?
yes.
Okay, I haven't seen.
sir, the problem is these questions are probably very easy, but in the exam you give complicated problems, difficult problems. Anyway, that was just a fun thing. Sir, another question: this estimator goodness, which is that expected value, where it comes up to sigma square into trace. Is there proof somewhere there, sir, or the derivation which we can look at?
No, I haven't looked in any proof of that. But to
Okay.
check that, I haven't looked for that.
Okay.
So when we're looking at this data set, can you scroll up a little bit, please? When you say cross validation on k-fold, all of them are data points. I mean, like each of them is data, right?
So we have divided into 10 parts. If you have 1,000 data points, you have divided into 10 parts. So each part will have 100 data points.
So it's only the points. We're not talking about how many features a point has.
No. It's only data points.
It's all the data points, 100 data points.
Everything has all features.
Okay.
So if I understood it right, because sometimes this is like that SGD thing, I got so confused. See, there are, let's say, 10 folds. We run the model on 9 folds and validate on the 10th fold.
10th
Then
fold.
next time we do it on another 9 folds and validate on the 10th. Then
10.
again 9. So it kind of goes in that round robin for 10 times.
10
So
times.
there are 10 folds, we run 10 models.
Yeah.
And 10 validations.
10 validations. So we are training 10 models for a particular lambda.
Correct.
Okay, so if there is no doubt, we can.
So somebody, one conceptual question, I'll just take 2 minutes. So somebody had asked this on the discourse, I think. See, the XXT is coming up again, which is the covariance matrix. And then we are getting the diagonal. Like there's no real role of eigenvalues and eigenvectors here, right? I mean, it just happens to be a covariance matrix because we're looking at covariance between features. But otherwise, there is no.
No, if you are comparing this with this particular lambda, it's nothing to do with those eigenvalues.
Yeah. That is clear. That lambda is different from this lambda. But I'm saying the fact that the covariance matrix is coming in, does that have anything to do? No, there's actually nothing. There's no connection with like the eigenvectors or
No, there's some connection, but we avoid this, and how we choose those using cross validation techniques. These are user set defined parameters, right? So it's nothing to do with those eigenvalues and eigenvectors. Okay, so actually, if you look at those higher values, we are calling this lambda as, right. So if you look at this lambda, we call it as 1 upon gamma square, right? We replace this constant by this constant, and this again is covariance of XX transpose plus something like that, right? Covariance of that. We assume we assume this to be the covariance of those
1 by lambda
0 1 upon gamma square, right? This we assume prior for W. So for in that constant, they may be they have some relationship, but not with the eigenvalues of that XX transpose covariance matrix. Okay, so this is the covariance of those covariances of those vectors, weight vectors, not of those XX transpose.
But this lambda is kind of related to the covariance matrix. That's what we're saying.
No, this lambda is not related to that.
Yeah, but in the map, it comes out to be 1 by sigma square, right, sir? So the lambda value comes out to be.
So yeah, 1 by sigma square, but this sigma square is we assuming covariance of the weight vectors, not for the XX transpose.
Covariance of the error vector, actually, errors.
Covariance of the, not error. Here we assume the prior, right? Prior assumption for the W.
Correct.
Remember, where we are calling it a Gaussian with mean 0 and this covariance.
Correct. So I'm saying we already have an estimate for lambda from here, right?
But we don't know this thing, right? Our target is to reduce this covariance. Not just always reduce, but we want this to such that if you reduce this thing, it means that your W vectors are going closer to mean, right? And what is mean? 0, right? So if you reduce the variance of this W vector, I mean, so here if you take this W assumption, we are assuming prior for W to be normal, 0, and some gamma square, right? So if you reduce this thing, so it means the variances of W vectors reduced. Think is as a one dimensional. Now you have only one weight vector which follows normal sum 1 upon gamma square. It is constant. So if you reduce this thing, it means that your weight vectors are coming closer to the mean, right? Zeros,
Correct.
right? So, and if we are replacing this by the lambda, so how much to reduce this? Reducing it, this means that you are increasing your lambda. So
Yeah.
increasing lambda means that you are actually shrinking your W's to the zeros.
Okay.
Okay, but you never know what this lambda should be. It depends upon the problem. Okay, so how to do that? We find this lambda using cross validation techniques. This was the point there.
Okay.
So it's
So
nothing to
basically,
with the covariance of XX transpose.
no. Sorry. I was thinking we are trying to reduce the variance, and that's the reason why we are going for.
Yeah, we are trying to reduce the variance. Reduce variance means that we are closing to mean expected values, right? This is the your mean for that.
Yes.
Yeah, so that expected value of the mean is 0. We've assumed we want to keep it around 0. So we are getting it to 0 as much as possible.
As much as possible by increasing your 1 upon gamma square, or say by decreasing 1 upon gamma square, or say increasing your lambda.
Yeah.
Hello, sir.
Yes.
So 1 second, sorry, Sampa. Gamma square is representative of lambda.
Gamma square is,
Representative of lambda.
but we have replaced this constant by lambda.
Okay.
That's it.
Okay. 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 Yeah. Sorry, Sampa. Please go ahead.
Okay.
But
Hello, sir.
Yeah. Yes.
Sir, in a problem, some eigenvalues of the matrix are given, and it is said that the eigenvalue of inverse of that matrix you have to find out. What will be the approach? I cannot.
Okay, eigenvalues of a matrix is given, right?
Yes.
So if eigenvalues of the x is lambda 1, what is the eigenvalues of x inverse?
1 by lambda 1.
1 by lambda 1, that's it.
Okay. Okay.
You can prove it. Those kind of questions you easily to prove, right? Because you can just write the eigen equation. If I'm calling lambda 1 to be eigen of this thing, it's just like x lambda 1 equal to lambda 1, not x lambda 1, x mu 1 equal to lambda 1 mu 1, right? Where mu 1 is the eigenvector. You solve for x transpose, you try to find out in the form of x transpose. So it's kind of you can write it as mu x transpose lambda mu, right? So if you think it will become x transpose mu upon 1 upon lambda mu, right? So 1 upon lambda is the eigen values corresponding to the same eigenvector, right? So if lambda i's are the eigenvalues of x, 1 upon lambda I have the eigenvalues of x in this. Such proofs are very easy, right? You just write the eigen equations and deform those and write into the nice form.
Thank
Hello, sir.
Yeah.
Yeah, there is no more numericals to be asked, and I have some doubts related to norms, sir.
Which norm? What is that?
Like we talk about L2 norms, right?
Yeah.
And today you also mentioned about L1 norms,
Uh-huh.
and I was just trying to figure it out in Google, and also I came to know that there can be, any like L3,
P
L4,
norm.
or
Yeah.
yeah, even L17th norm or L20th norm. So
So
what
P
is
norm.
meant by,
Yeah.
so
So
what
P
is
norm.
yeah? So what is meant by norm actually, sir? Because my layman understanding so far is that norm is nothing but length of a vector, right?
Yeah, so this also comes from your knowledge of the vector space. So norm, you define norm is very define a vector space where you define some norm as a function from some vector space to vector space. Like I mean the vector space to some real number. So this is your vector space to real number. It
Sir,
follows some properties.
basically,
what I will request, sir, if before getting into the mathematical definition,
Hmm.
let us understand it intuitively. Then we'll get into that, vector
So
space to
all
vector.
norm you
Like,
think you can think as a basically.
no, for length of a vector, that part is clear to me because this I had asked in MLF session also, but that was not answered, and it was told to me that it will be get answered, in higher courses.
Okay.
But I may be, I'm still struggling
so
to understand.
GP, let me try if this helps. See, typically in all this we are talking about the Euclidean space, right? Which is basically x, y, z, right? So here norm typically translates to the distance
Right,
vector.
right.
But actually, if you have to generalize that, norm is basically the dot product of the vector with itself. Square of the norm is the dot product of the uh, or the inner product. The right word is inner product of the vector with itself. Now it depends on how you define that inner product. In Euclidean, this thing, the inner product is dot product. It could be anything. For example, xy inner product xy could be x cube plus y cube by x minus y square. You can define it whichever way you want, as long as that norm, as that dot product, inner product obeys certain rules, right? So depending on how you define the inner product, the norm calculation also changes. In Euclidean, it turns out to be just the distance measure.
So Basu, that's exactly my problem because in maths too, we had studied about that inner product, function. It will be
Correct,
defined.
correct,
It will be defined in a certain way, right? And then we have to
correct.
check. Then we have to check for certain conditions, and then we have to justify. Yeah, inner product is satisfied. But those are very mechanical. I'm just trying to understand the conceptual part of it. So, no, what forces us to change the definition? Like in Euclidean space, as you rightly said that this is called, length of the or the distance of the point from the origin, right? That's what we mean, right?
Oh,
So all of
oh.
a sudden we started calling it as a norm, and then we are saying there is something called L1 norm also, L2 norm also, and then can be L17, there 20th norm also. That part, it may sound very trivial question at this stage of the course, but I'm
No, you're
still not.
right.